Hey guys, today we're going to be explaining how to represent pointers in memory, how to visualize pointers, and finally why we need them with examples. So first off, we need to understand the difference between two types of memory, dynamic allocation and automated allocation. So first off, let's dive into automated allocation. So automated allocation is usually what you're used to, and it comes from the stack. So when you declare a variable as shown below, int num is equal to 2, when you create this, it's declaring and defining this data from the stack. So let's take a deeper look onto what each definition actually means. So when we say something like declare, it means that the compiler is assigned a symbol. So once this symbol is assigned, the compiler knows this variable is in play. And once we define it, it's eventually allocated in the memory, meaning it's created so we can actually store a value. In terms of this memory, we're using the stack. What the stack allows us to do is it's automated by the system and cleaned by the system. This means when you create this variable specifically, it's automated, so you don't have to do anything besides create it. So it's created and disposed of by the system. So now let's move on to dynamic allocation. This is a little different because you're still able to find and allocate memory as shown previously. However, this time the memory is automated and disposed by the programmer. So when you create this memory, you usually get it from the heap. It allows you to create and access this memory yourself. So you have to make sure to take care of this memory as it feels like your own child, for instance. And if you don't dispose of this memory once it's done, then you're going to get things such as memory leaks, which can allow for data breaches and people to just access your memory or even corrupt your program yourself. So now that we understand the memory portion of pointers, let's take a look on how variables are represented to understand pointer syntax. So a variable is an addressable container in memory that holds a value. So let's take a look down below. So we've seen this before, this syntax, int num is equal to 2. And a great way we could visualize this is by showing it in a container. So in a container, we create some type of box that holds some value, which is the number 2, for instance. It contains some type, which is an integer, as well holding some type of address. So you may be wondering, why do we have these addresses? Well, imagine this container as a box. If if this box, if you wanted to find this box, you would need to supply it either some name or some address, just like a house as well. So if you're in a neighborhood and you're trying to find some house, for instance, the only way to really find it is by its house address. If not, you would have to drive everywhere and then eventually see if you could even find it. So that's a great example and analogy where you could put this on why we need addresses. It's just to allow the compiler to locate this memory and see where to allocate it. So now let's move on to pointer syntax and how pointers are actually used. So as shown below, this is just a basic description and template on how pointers are usually addressed and showed. So just like any variable, it has some type, includes an identifier, but this time it's going to hold an address. We're going to go a little more later on why it actually holds an address, but this is just a syntax for now. Usually you may see this symbol right here. It's like an asterisk. It basically combines with the type. It's basically telling you that we're going to hold an address of an integer. So this address could be anything. It could be like OX10, OX11, OX11, OX12, anything you like, as long as it's an integer. If it's not an integer, you're probably not going to be able to hold it. So now that we provided an identifier as well as the type, we can now assign it any address. So now you may be wondering, okay, there's addresses, but how do we actually access the addresses? So as shown below is more syntax, and we can see we're creating some regular variable, this time from the stack this time, and we're gonna assign it an address. This address comes from this identifier specifically. So we're basically accessing num. So imagine down below, this is a great visual to see how this is working, is there's a box as shown. It contains an address. But note, this address is not its own address, it's holding an address. This is a value, and it's holding the address of num. This one is num. And as shown above, we can see that we're able to access this num using the reference or the address of operator. This basically gets the address of any data and it allows you to see the address so you can assign it to the pointer. So another way we could create this, let's create this again. So if we were to start, we want to create the pointer as a variable. So let's create a box, create it as so, and we're not going to assign a value yet, but let's see what the type is. The type is int pointer because it's going to be holding a pointer. And with that, we need to assign an address itself. Imagine, again, this is OX20, and this is the box, or we could think of this as a house. Now we need to assign an address. So this is what this is doing. So when we do all of this syntax, it's creating this box right here. But when we assign the address, it's getting placed inside of the box. So we can put OX10, for instance, and now it has a relationship with num. This is usually called a level of indirection. So it's basically a pointer to an int. This is a level of indirection right here. So if we create the other box now, which is shown above right here, this would be displayed as another box. We know its type int because it's an integer. It has an address of OX10 and has a value of 2. So now that we've created this relationship, we can point an arrow to it. This is just a good way to visualize it. You don't actually have to point an arrow inside of the memory or when you're actually coding. It's just a great way to visualize the relationship between a pointer and another variable. So now that we understand this relationship, we're going to see how to actually access these values. So as shown is the syntax we've seen earlier. And when we created these values, we created this relationship above. So now, when we do this, for instance, we're couting. So we're using the standard out and using one of the direction operators, the insertion operator, to go inside the standard out. So when we just display num pointer itself, you may be wondering, okay, it's going to display the actual value, the number 2, because it's pointing. However, just like any variable, when you cout, it's going to display its own value. So for this instance, num pointer is going to display OX10, as shown in the standard out below, right here. So if we go down one more step, we see it cout, this time with the asterisk again. The asterisk has 2 meanings. It means it's a pointer as well as a dereference operator. It just depends in the context. In this context, we're dereferencing it, meaning we're dimming down the level of indirection. So for instance, when we say pointer to int, when we apply this dereference operator, we're basically cutting off a level of indirection. This means we're erasing the pointer part and the arrow, and now we're becoming the int. So now that we are the int, we're able to display it. So we have the value of 2. This is equal to the value of 2 right now. So as shown above, it's going to display the value of 2 right there. Okay, now that we understand the basics of pointers, you may be wondering, what is really the point of it? We're able to get the address, we're able to have a value, but why do we really need this? So I'm going to give you a scenario to imagine. Imagine we're at a grocery store and we make a list, right? This list can be represented as an array. And we have 10 items. This means we have 10 indexes. However, we need to add 2 more items to the list. So, as before, we know an array is a contiguous block of memory. This means in memory, it's in a single line. It's all together. All of this memory is together and it's harnessed. However, if we want to add two more values past 10, so we add two more boxes to create 11 and 12, we would need to create a whole new array as above. It looked like this: int num 12, and then any listings you provide. So this would take forever and it would cost a lot of space because you need it to be contiguous, a whole bunch of numbers together. However, imagine we had 1,000 items. If we had 1,000 items, it'd be almost like impossible to find an area of memory where we could hold all of this data. So that's where we introduce things like pointers. You can read this above to understand a little more in depth on what I was explaining. But basically, pointers allow us to point to the next data, and this data contain data within itself. So for instance, right here we're making some type of class or structure. It contains some name, which is the item, and it contains the next pointer. So we can label this, for instance, as node pointer. So node would be considered this whole structure, for instance. And if we want to point to the next structure, we're going to have to use the dereference operator to access the value, the next value, Coke, for instance. So as you can see, we're able to continually access data infinitely. This means you can add nodes and it's not contiguous. It can be anywhere in memory. So let's take a better visual of this. Imagine we had a block, right? And this is in the RAM. This could be in the stack, for instance. So we have blocks, we have a whole bunch of lines as shown below, and we need to create an array. An array, it take up this whole block of memory right here. However many items this is. It could be 1, 2, 3, 4, 5, 6, 7, 8. 8 blocks. This could be 8 items, for instance. But if we wanted to create a new array, we would have to just say, for instance, create a new contiguous block of memory. So it'd be all the way over here, include some of these, and it would take up all of these boxes. And we would continually have to do this every single time. And that would be a little tedious. However, in the instance where we allocate memory from the heap and create pointers, we can do something a little more different and a little more efficient. This time, if we have another box, we can display memory throughout the RAM. So we could have a block over here, could be 1, a block over here could be 2, a block over here could be 3, here 4, 5, 6, 7. As you can see, they could be scattered. However, using pointers, you're able to link all of these nodes. So you go 1, 2, this line could go 3, 4, 5, 6, 7. And you don't need to create a contiguous block of memory. It's dynamic, which means it's always changing. So it allows you to create something that's simpler, or it may seem a little more complex right now, but the more you do it, it gets easier and easier. But it's more efficient and it allows you to really understand how the memory works and allows for ease of access of memory. So that's the basics on what pointers are, how to see them, how it's represented in memory, and how you can really grasp this concept. Thank you.